This is AP Calculus AB, and this is the video for section 6.1, estimating with finite sums. So in this video, we're actually starting the second semester, and we're starting to shift into the concept of integration. So what we're looking at today is really the basis for how integration actually works. When you look at the calculations that we're going to do today, you're going to see that they're very, very simple. So I don't want you to focus on just doing the calculations in this section. I want you to really try to focus on conceptually what's happening when we do these calculations, because that is going to help understand how an integral works. And it's also going to help you understand how everything works when we get into applications of integrals. So try to keep those things in mind when you look at this stuff that we're going to do in this section, because like I said before, the calculations themselves are going to be very, very simple. We're just going to be finding the areas of rectangles. So this section is called estimating with finite sums. And what we're looking at here is a velocity graph. And let's say, for instance, from this velocity graph, we wanted to find the distance traveled. You can see that the velocity here is constant at 75 and 75 miles per hour. And we have a time interval here from 7 to 9, so 2 hours. So if we had a constant velocity of 75 miles an hour for 2 hours, pretty clearly we would go a distance of 150 miles. Well, that 150 miles is actually what the area of this square is, or actually this rectangle. It looks like a square, but it's actually a rectangle. So you can see the base is 2 and the height is 75. So that's essentially what we're doing when we take an integral. We're finding an area between a curve and the x-axis. Well, that's pretty easy to do when you have really, really simple constant functions like a constant velocity. Most of the time, though, when we are using integration, it's because we have a situation where our function is not constant. So if you look at this graph, this is more along the lines of what we would typically see when we're trying to solve an integral. So we have a velocity. This time it's varying with time, and you can see we're looking at some time interval from A to B. Well, if we wanted to know the distance traveled, the distance, just like on the last one, would be whatever the area of that region is. The hard part is, how do I find that area? I don't have a simple geometric formula. I don't have an easy way to solve that out. So what we're going to do is we're going to break that area into smaller intervals. So we had the interval that went from A to B. Now we have these smaller intervals that we're going to call subintervals. And within each one of these subintervals, we can do an approximation for the area of each one of those subintervals. And what we're going to use to approximate those areas is we're going to approximate it with rectangles. So at the top of each one of these intervals, I'm just going to put in a rectangle height. And you can see that in some of these intervals, I've got a situation where I'm really, really close to the area between the curve and the axis. And some of them, it looks like I'm underestimating pretty badly. But this is what we call a rectangular approximation. And this is going to be our focus for today. So if I were to get enough of these subintervals, if I were to keep increasing the number of subintervals, I would find that there was less and less error in that calculation. And eventually I could approximate and approach exactly the value between the curve and the axis. Okay, so like it says here, that region is partitioned into vertical strips. And when we make those smaller and smaller and smaller, that's going to allow us to get the exact area between the velocity curve and the axis, which would give us the distance. Okay, so we're going to go through a couple of examples here where we use a small number of subintervals, and I'm going to show you how this extends into the idea of an integral, which is what we're really focused on. We have this velocity function here. It says a particle starts at x is 0 and moves along the x-axis with velocity t squared for time is greater than or equal to 0, whereas the particle at time is equal to 3. So if I were to find this area underneath this velocity curve, the area of that region would represent the distance that I've traveled in the x direction, and that would tell me where the particle is at time is 3, because we've moved in the positive direction and we started at a position of 0. So again, we don't have a way right now to calculate this exactly. So what we're going to do is we're going to approximate this by using subintervals. And we have 3 different methods that we can use for this. And the methods that we're going to use are going to be what we call a left-hand approximation, a right-hand approximation, and a midpoint approximation. So I'm going to start with this first one. It's called LRAM, and what that actually stands for is a left-hand rectangular approximation. Okay, so this is a left-hand approximation. Okay, so that LRAM is left-hand rectangular approximation method. So we're typically not going to write LRAM. I'll show you some shorthand we'll use here in a second. But you can see on this diagram what we're doing. We are taking whatever the function value is on the left side of the subinterval, and we're treating that as the function value for the entire interval. So we've broken this interval from 0 to 3, from time is 0 to time is 3, we've broken into 6 subintervals. So we essentially have 6 rectangles here that we're going to try to use to approximate the area underneath the curve. And it's pretty obvious here. I'm underestimating because I'm missing area here, I'm missing area here, I'm missing it here. All of these are underestimating the area underneath this curve. But it's a good rough approximation to give me a feel for how this is going to work. So down below here, I'm going to write out my left-hand approximation. So we're going to do the left-hand rectangular approximation method with n is equal to 6. And that is the number of subintervals. Okay, so when I do this left-hand approximation, here's how I'm going to write it out. First of all, L6 means I'm using a left-hand rectangular approximation with 6 subintervals. And so this is going to approximate the distance that this object has traveled. And the way I'm going to approximate that distance is just by doing base times height for each one of these rectangles. So for the first rectangle here, you can see that if I were to do the left-hand side of this subinterval, I'm looking at this interval right here. So the length of my subinterval is 1/2, so that's the base of my rectangle, and the height is whatever the function value is on the left side of that subinterval. So remember, this was velocity is t squared. At time is 0, I'm going to have a function value of 0 because it would be 0 squared. Now the next subinterval goes from 1/2 to 1. So the way I'm going to approximate that is 1/2. The left side of the subinterval is at time is equal to 1/2. So plug that into my function, 1/2 squared, and that's going to be the area of the second rectangle. Now the third rectangle goes from time is 1/2 to time is 1.5. So I still have a base rectangle, or the base of the rectangle is 1/2. The height now, the left side between 1.5 and 1 would be 1. So I plug that into my velocity function, 1 squared, and then we're just going to continue on all the way through the 6 rectangles. So the next one, we're going from 1.5 to 2. 1.5 is 3/2. Plug that into the velocity function, it gets squared. Then we're going to go from 2 to 2.5. Plug that into the velocity function, it's 2 squared. And then for the last rectangle, we're between 2.5 and 3. 2.5 is 5/2. Plug that into that velocity function, and it gets squared. So all I've done there is added up 6 rectangles, the areas of 6 rectangles. Very, very simple to do. And it turns out for this, when we do our left-hand approximation, we're approximating the distance, which is where the particle would be at time is 3. We're approximating that to be about 55/8. And I'm going to write this as a decimal just to make this easier to compare the 3 methods. So we get about 6.875. Okay, so obviously it was an underestimate, but it gives us a general idea of the distance that this object has traveled in the first 3 seconds. Okay, so that was a left-hand approximation. Well, I'm going to skip to the right-hand approximation first, and I'll come back to the midpoint because the midpoint's just a little more complicated. So for the right-hand approximation, sometimes you'll see it referred to as LRAM, but that's a right-hand rectangular approximation method. Okay, so let's go down here and go through the same process. So everything is a lot like it was for the left-hand approximation, but one slight difference. Okay, we still have n is equal to 6. This time, I'm going to use R6 to represent a right-hand approximation with 6 subintervals. And for my distance, going to work essentially the same way. The base of each rectangle has a length of 1/2, but this time to get the height of each rectangle, I'm using the right side of each subinterval. So the first time interval goes from 0 to 1/2. So the right side of that subinterval is at 1/2. 1/2 squared would be the function value. So that's the height of that rectangle. The second rectangle would go from 1/2 to 1. The right side of that subinterval is 1. And then we're going to continue on that process. Then from 1 to 1.5, so I'm going to get 3/2 squared. Then from, let's see, 1.5 to 2, so I'm going to get 2 squared. And then from 2 to 2.5, so that's going to give me 5/2 squared for the function value. And then the last rectangle has a base of 1/2, and it goes from 2.5 to 3. The right side of that subinterval is at 3, so that would be my last rectangle. Notice we have 6 rectangles again, just base times height every time. This time though, when I add this up, my distance is approximated to be about 91/8. Well, that turns out to be about 11.375. That's a lot different than the first approximation that we got using a left-hand approximation. But take a look at this graph on the right-hand approximation. Look at all this extra area that we have above the curve that we're counting when we do this right-hand approximation. We're really overestimating pretty dramatically, and you can see that, and you can see in the result that we got a number much, much higher than what we got for the left-hand approximation. So both of those were pretty far off from the actual value. The left hand was underestimating by a lot. The right hand was overestimating by a lot. We have one more method we can use, which is called a midpoint rectangular approximation. Okay, so this is a midpoint approximation. So LRAM would be midpoint rectangular approximation method. And you can see on this one, what we're doing is to find the height of the rectangle, we're using the function value at the midpoint of each subinterval. So you can see on this, it looks a lot more accurate because, like, for example, here I've got missing area, but I also have extra area. Missing area, extra area, missing area, extra area, and so on. So a lot of this is going to sort of balance out, and this is going to give me a pretty close approximation for the actual area underneath the curve. So we're going to go through the same process here. And to do this, the only thing that's a little tricky on this one is we have to approximate, or excuse me, we have to calculate where the midpoint is each time. So we're going to do midpoint rectangular approximation method with n is equal to 6. I don't usually write that out. Usually I would just write m with a subscript 6, indicating we're doing midpoint rectangular approximation with 6 subintervals. So my distance this time, it's going to be approximated. My base of my rectangle is still 1/2, but now to find the height of each rectangle, I need to go to the midpoint of the subinterval. So the midpoint of the first subinterval, between 0 and 1/2, the midpoint is 1/4. So that's what I'm going to plug into my function. The next one goes from 1/2 to 1. Midpoint would be at 3/4. Then I'm going to go from 1 to 1.5. The midpoint would be 5/4. And then you can kind of see a pattern here. Then we're going to go to 7/4. I've got to square these each time because I'm getting the function value. Then I'm going to go to 9/4. That would be the midpoint between 2 and 2.5. And then the last one between 2.5 and 3, that would be at 11/4 or 2 3/4. And I'm going to square that because that's my function value. And now I've got my 6 rectangles. And if I were to calculate this one out, we would find that the distance that we found, that we approximated, was about 143/16. And that's actually about 8.9375. Okay, so those are my 3 approximation methods. Now, you can see we got dramatically different results each time. I know that the midpoint approximation is the closest to the actual value. Now, I want to show you how this sort of turns out. I did include over here some information about doing this on the calculator. You don't have to know how to do this, so I'm not even going to spend time going through this. I just want to point this out. there are some questions in the assignment where they might ask you for a larger number of subintervals. And so they might ask you for like 50 or 100 subintervals. I don't want you to try to calculate that out by hand. So the intent there is for you to use a calculator to do it. And your calculator doesn't have a rectangular approximation method built into it. Some calculators do. So if you want to work those out where you're getting 50 or 100 subintervals or a large number of subintervals, this is essentially what you would have to do. But I'm not going to ask you to do this. So if you want to learn how to do it, that's fine, but it's not something you have to know how to do. Okay, so what I do want to talk about is if we did go through and look at this same problem with larger numbers of subintervals. So this is what we just calculated. N is equal to 6. So let's say we started increasing the number of subintervals. Notice what happens as I'm going in this direction. My left-hand approximation is getting higher and higher and higher and higher, and it looks like I'm getting really, really close to 9. My midpoint approximation started out pretty close to 9, but again, I end up really, really close to 9. And with the right-hand approximation, I started out above 9 significantly, but you can see I'm decreasing and getting closer and closer to 9. So eventually what would happen is if I took the limit as the number of subintervals approached infinity, all three of these methods would converge to the same value. They would all approach exactly a value of 9. And that's actually what we're trying to get at is if we were to actually solve an integral out, that's what we would be doing. We'd be taking the limit as the number of rectangles approached infinity, and then we could get the exact value of the integral. So I'm going to show you how this would work because this is kind of where we're heading with this. So what we would do with this is we would actually take the integral from 0 to 3 of t squared dt. So there's some notation here you may not have seen before. That's integral notation. Tells me that I'm integrating the function t squared on the interval from 0 to 3, and I'm integrating with respect to t. So if we were to solve this out, we use what's called an antiderivative. The antiderivative of t squared is t cubed over 3. And then we get into something called the fundamental theorem of calculus, where we have to take the antiderivative at the upper limit minus the antiderivative at the lower limit. And you would find that this is 3 cubed over 3 minus 0 cubed over 3. And that's exactly equal to 9. And notice the value that we were seeing that we were approaching for all three methods, left-hand, right-hand, and midpoint. They were all approaching a value of 9 because what I just did was I just solved it as if we had an infinite number of rectangles, and I got the exact area under the curve, which is exactly equal to 9. So like I said, this part that I showed you right here, you don't have to know that yet. I just wanted to show you why we're going through this process with the rectangles, because we're trying to understand what's happening when we actually go through and solve an integral out. Okay, so let's take a look at just a couple more examples. So on this next one, I'm going to do this with some shorthand notation to make this a little bit easier. It says a particle starts at x is 0 and moves along the x-axis with velocity t squared plus 1 for time greater than or equal to 0. Where is the particle at time is 4? Approximate the area under the curve using 4 rectangles of equal width and heights determined by the midpoints of the intervals. So we're doing a midpoint approximation. So our area is going to be approximated by a midpoint approximation with 4 subintervals. Well, that midpoint approximation would be given by this. So I know I'm going from 0 to 4. That gives me 4 subintervals on the interval 0 to 4. Each one of those rectangles is going to have a base of 1. So what I'm going to do is I'm going to factor the base out. If you think about over here on these, the 6 subintervals that we just did, each one of these, each time, notice it had a base of 1/2 every time. So what I could have done to save myself a little bit of writing, knowing that the base was always the same, is I could have factored the base out. And that's what I'm going to do this time. I'm going to factor the base out. And now what I'm going to put inside of here is I'm just going to put all of the heights of my rectangles. So my function is t squared plus 1. My first subinterval goes from 0 to 1. That means the midpoint is at 1/2. So if I wanted that function value, my function value is going to be given by t squared plus 1. So that means I'm going to do 1/2 squared plus 1. So that's my first function value. So if you distribute the 1 base times height, that gives me the area of the first rectangle. Now for the next subinterval, I'm going from 1 to 2. So the midpoint would be at 1.5 or 3/2. We're going to square that and then add 1 because that's what my function is, t squared plus 1. Next subinterval goes from 2 to 3. So the midpoint's at 2.5, which is the same as 5/2. We're going to square that and add 1. And then the last rectangle is between 3 and 4. So the midpoint's at 3.5. So I'm going to do 7/2. We're going to square that and add 1. Okay, so that would be my midpoint approximation with 4 subintervals. 1 times each one of those heights gives me all 4 of the rectangles. So in the end, my midpoint approximation, the area that I'm approximating, the area between the curve and the axis is about 25. And that means that it says approximate the area under the curve using 4 rectangles. That means that my position at time is 4 would be approximately 25 units to the right of x equals 0 because that's the area between the velocity curve and the time axis. Okay, so that's how I would prefer you write your work when you have to write out the work for these problems. I know when you're doing your Math Excel homework, you don't typically have to show work, but when you're writing it out, try to practice writing it out in this form so that when you have to do it on a quiz or on a test, you've been practicing the format that I would like to see. Okay, so let's take a look at just a couple more. It says true or false. The left-hand approximation is always less than or equal to the midpoint, which is always less than or equal to the right-hand approximation. So let's think about whether or not that's always true. And it says, let's consider this function, 5 minus 4 sine x over 2. And it looks like we're looking at the interval, maybe from 0 to about 2.5, close to 3. So let's think about a left-hand, a right-hand, or a midpoint approximation. Let's take a look at the graph here. So for the left-hand approximation, you can see in this case, because it's a decreasing function, the left-hand approximation is actually overestimating because the highest value on each one of those subintervals occurs on the left-hand side. So you can see all of these rectangles are above the actual curve, and that's giving me a bunch of extra area that I would have to work with. Well, if I did a right-hand approximation, I'll do it in blue. You can see with a right-hand approximation that I'm actually down below, and I've got a bunch of missing area. And then obviously with a midpoint, we're going to be somewhere in between. So the midpoint's in the middle, but the main thing is the left hand actually was the highest of the values this time. So this is actually false. This is not always true. It depends on whether your function is increasing or decreasing in terms of whether or not you're going to have the left hand or the right hand as the highest value. If it's a decreasing function, the left hand approximation will be the highest. If it's an increasing function, then the right hand approximation will be the highest. Okay, so last example that I wanted to show you here, this actually gets into something that we're going to do at the very end of the new material we're going to cover this semester. This gets into the idea of approximating volumes. So this is one of the applications of integrals that we're going to look at. But we can actually do this in a really basic way right now using the same idea as a rectangular approximation. So it says we're going to approximate the volume of a sphere with radius 4. And what we're going to do is we're going to slice this sphere up into a bunch of thin slices, and we're going to say each one of those slices can be approximated by the volume of a cylinder. Well, the volume of a cylinder, right, is pi r squared h. So volume of a cylinder is pi r squared h. Well, what they did was they said, okay, well, the radius is essentially going to be, if I were to draw in a curve here, that would be a semicircle, and the distance from the x-axis up to that curve would be whatever the function value is for the top half of the circle that would form the entire sphere. Okay, so knowing that to be the case, there's my radius. My radius is the square root of 16 minus x squared. The height of each one of these cylinders is whatever dimension I have going in this direction. Okay, so what we're going to do is we're going to use 8 subintervals. So we're going to use n equals 8, and we're going to use a midpoint approximation. So we're going to do a midpoint approximation with 8 subintervals. Okay, so let's talk about how we would do this. For our volume approximation, since we're using 8 subintervals, this would go from -4 to 4. Well, for each one of these subintervals, we would have, if we're going to use 8 subintervals from -4 to 4, we would have a height of 1 for each one of these cylinders. So I'm going to factor out what every cylinder would have in common. They all have a pi in the formula for the volume. They all have a height of 1. So what changes each time is the r squared value for each one of these cylinders. So what we would have to do is find the midpoint of each one of these subintervals. So the first one, using my function, 16 minus x squared is my radius. My first subinterval goes from -4 to -3. So the midpoint would be at -3.5. So I'm going to do 16 minus -3.5 squared. And then remember, since it's a radius, we're going to square that value. Then the next subinterval goes from -3 to -2. So the midpoint's at -2.5. So it'd be 16 minus -2.5 squared. And then that's a radius, so we're going to square it. And we would continue going through that process all the way through the slices that we have. And when we get over further to the right between 2 and 3, the midpoint would be at 2.5. So we'd have 16 minus 2.5 squared. And then we'd have to square that because it's a radius. And then for the last one, between 3 and 4, we'd have 16 minus 3.5 squared. And then we would have to square that because it's a radius. And that would be my volume approximation. Now, I didn't show every single one of those. You could easily write out every single one. I just did it for the sake of efficiency here talking about this. But we could write out all of those and then plug them into the calculator. And what we would find is that our volume is approximately 86 pi. Now, that's not actually the volume of a sphere with a radius of 4, but you could check that pretty easily if you did volume. Volume is 4/3 pi r cubed. You could do that as kind of a check and say, okay, is my answer very close to 4/3 pi r cubed? If it is, I know I did a pretty good approximation. Okay, so that's kind of the idea. We can do volumes with this, even though we're just doing this idea of rectangular approximation. So I did include some more information about doing this on the calculator if you wanted, just to show you this one. And let's say we wanted to do more slices to get a more accurate representation. We could do this on the calculator, and then we could add up 100 slices. Because obviously, if we had 100 subintervals, we wouldn't want to write out this expression that I have here with 100 subintervals. That just becomes too tedious, and it's not efficient to solve it out that way. Okay, so most of the time on your assignment, you're going to have subintervals, numbers of subintervals that are relatively small. So it'll be pretty easy to do. But keep in mind, there is that stuff with the calculator if you want to investigate it. Okay, I also included a worksheet here. This is not something you have to turn in. I included this in case you wanted to have something where you actually draw in the rectangles to get a good, clear vision in your mind of exactly what's going on when we do a right hand, a left hand, and a midpoint approximation. So you can go through this worksheet if you want. I have the solutions for it posted on my website, or excuse me, on Schoology, so on the Schoology page. So if you want to work through the worksheet and check it, you can easily do that. Now, this is only the first day of section 5.1. We're going to spend another day on this section next time. We're going to talk about how we can write out things like this more efficiently using what we call a summation notation. So we'll talk about that on the next video.